So now we're going to look at how we can visualize a function and its derivative and what's happening. So here we have a function f of x equals the sine of x over x. We want to actually find out what big F is equal to, the antiderivative. So we want to know what the antiderivative of this looks like and what it is, but unfortunately this doesn't have an antiderivative. Sine of x over x is one of these functions that does not have an analytical antiderivative. It has an antiderivative, it's just we can't find it analytically. So we have to look at is we're going to do what we call slope fields. And slope fields are where we're going to actually find the value of f, this function little f, at different x values. So x of 1, x of 2, x of negative 1, x of negative 2, 0. Well, obviously not 0 because 0 would make it undefined, but all these other ones that we could do. So you can look at all of these values and see what's going on. And from that, we can then graph what the derivative function looks like. And from that, we can then get the function. Because remember, the derivative function looks like it's the slope of the tangent lines. It's the slope of the curve. So if we could graph up these derivative function, this derivative function of sine x over x, we can actually think about what does the original function, the antiderivative function, look like that matches up with those tangent lines. This is not easy to do by hand, so we're going to actually use technology to do it. So let me bring up Desmos. Why is this not working? Okay, there we go. All right, so this is a slope field generator that's in Desmos. We actually don't want the one that's here. This is for a derivative of 2x over y. We actually want a different function. We want the sine of x over x. So we'll just modify the one that they have in here for the one we want. So our function is sine of x over x, and this is what it looks like. So this is what the function looks like. We're going to then graph our original function, our antiderivative, from this derivative. So you can kind of see that each one of these little tiny lines is the slope of the tangent line at those points. We draw just a tiny little bit because it's only right near that point that it's the slope of that tangent line. So right near this point, that's the slope of the tangent line. Right near this point, that's the slope, and so forth. So we just draw a little tiny line. This is known as a slope field. We're going to go ahead and put this into where we are so we can work with it a little bit. So I'm going to take a picture of it. And we'll paste it into where we are. And there's our slope field for the sine of x over x. Now, the other thing we notice on here is that we do say we want f of 0 to be 0. So that's telling us where we're starting. So we're going to come here to f of 0, 0, and that's where we're going to start a point. And there's my point right there. And then what we're going to do is we're going to kind of draw from this point, kind of following these tangent lines. So think of it, you're kind of coming up and meeting up with that tangent line. Then you notice this one turns, and then it kind of flattens out a little bit. Then it goes down. It goes down a little bit more. And it kind of flattens out. And it kind of goes up and down a little bit at this point. If we went the other direction, we notice it's going, what? It's actually going up, but we're drawing down at this point. We're going to come down through this. It flattens out, goes up a little bit, flattens out, goes down a little bit, and then flattens out, and keeps doing that. And there is the antiderivative. And so we can't find it analytically, but we can in fact find it graphically. So that's one other application. Another application I want to show you is a physics application. In physics, you have these wonderful equations for motion, and I want to show you where they come from. And so this one says a stone is thrown from a cliff, up from a cliff, with an initial speed of 20 meters per second from a height of 150 meters. find the height and velocity and acceleration functions. We are going to ignore air resistance. Air resistance becomes much more difficult. You actually need a course called differential equations to solve these if you don't ignore air resistance. So we're going to ignore it for right now. Most physics classes do that at the start too. So it's okay that we're doing that. And we want to find, after we find those equations, we're going to find the maximum height and when the stone hits the ground. So we have to think about where we're going to start. Let's start with what we know. We know the initial speed. So we know the speed at time 0, because that would be your initial speed, is 20 meters per second. We also know the initial height, if we call y height. Then we know, and v is velocity. And let's do a is acceleration. And so we also know the initial height. So height at y times 0 is 150 meters. And that's pretty much all we know. But there is actually one more thing that we know. You may not know this from if you don't know a little bit of physics, but if you know a little bit of physics, you know that on the Earth, the acceleration due to gravity is constant. Well, mostly constant. It changes depending on how far away you are. So your elevation, if you live at Flagstaff at an elevation of 7,000 feet, your acceleration due to gravity is a little bit less than if you were down at sea level. Not enough to really make a big deal, but it is a little bit less. But most of the time it's pretty constant, especially when you are at this height that we're talking about here. So we're going to look at, we know the acceleration due to gravity. The acceleration, therefore, is a constant. It is equal to the minus the acceleration due to gravity, which is g. So g is our acceleration due to gravity. In the metric system, which we are because we had 20 meters per second and 150 meters, g is equal to 9.8 meters per second squared. The minus sign is because gravity is pulling down and down is a negative. So we use that. So we have this idea, this is acceleration. Remember, acceleration is the derivative of velocity. It's a second derivative position. So you could actually think of this as s double prime is equal to minus g, or v prime is equal to minus g. And so we basically have a differential equation here that we're going to solve. So let's go ahead and find out what v is. V would be the antiderivative of v prime. So it's the antiderivative of minus g. So it's going to be minus g times g, the constant. So g is 9.8 meters per second squared. It's a constant. Like I said, it varies slightly on the Earth, but it's pretty much a constant. And so it's just like having a 3 sitting there. So you just take the antiderivative of minus g, your variable t in this case, because we like t for time. So I will say t equals time. Your variable t is t to the 0. Add 1 to that, you get t to the 1. So you get minus g times t plus some constant. Don't forget that constant. So let's call that just c. In physics, they call c v sub 0, and that's okay, because we can actually find out what that is. We can find out what that c is, because we now have v of t is equal to minus gt plus c, and we know that c, that the velocity at time 0 is 20 meters per second. So we can actually say that v of 0 is minus g times 0 plus c, and that equals 20. And it was up, so that's why it's positive 20. So that means c is equal to 20. That's why sometimes in physics, they just call c your initial velocity, because usually it is just your initial velocity. So we now have that v of t is minus gt plus 20. If you want to put v0 there, that's fine. In fact, let's go ahead and do that, and then we can actually see that we're going to get these equations. So we'll call this v0. So this way you can actually see where those equations come from that you've seen in a physics class. So now that we have v, let's find our height. Our height was y. Y is the antiderivative of v, because v prime is y prime is v, so the antiderivative of v is going to be what y is. So just to remind you, y prime is v. So let's take the antiderivative. So remember, you add 1 to the power, and then multiply by the reciprocal of the power. So you get minus 1/2 gt squared plus V0 again is a constant. It's 20, but it's just a constant. So think of it as you got t to the 0, add 1, you get t to the first. Plus some constant. We don't want to call it c, let's call it d. And again, we can find that because we know the height at time 0. The height at time 0 means you're going to put 0 in for everywhere you see a t. And that was equal to 150 meters. So that tells me d is 150 meters. By the way, d also in physics, they call that y0. So d is also the y0, the height at y at time 0. So we usually call that y sub 0. So we now have that a is equal to minus gt, minus g, v of t, and this is actually a of t. Even though a is pretty much a constant, we do call it a of t. V is minus gt plus v0. And we now have that y of t is equal to minus 1/2 gt squared plus v0t plus y0. So if you've ever wondered where those equations came to in physics, this is where they come from. This is exactly where they are. Now we're going to go ahead and put in the numbers we have in this case because we want to solve some things. So a of t was equal to minus 9.8 because g is the acceleration due to gravity is 9.8. V of t is therefore equal to negative 9.8 t. V0 was 20, and it's positive because it went up. Y of t was equal to minus 1/2 g, which is negative 4.9 t squared, plus 20t plus 150. So there's my equations for this exact situation. Now, we'd like to know, so those are the first, that's part A. In part B, we would like to know find the maximum height? Well, the maximum height, remember, is when the velocity is 0. Because we're looking for maximum, so you can take the derivative of your position to find out your velocity, and that would give you, when your velocity is 0 is when you're going to have either maximums or minimums. So to find out this problem, to find out your maximum height, that'll be when your velocity, which was negative 9.8 t plus 20 equals 0. So that's going to be t is equal to 20 divided by 9.8. Now we can take out a calculator and find what that is. So that's 20 divided by 9.8. That's about 2.04. 2.04. And it's seconds, so we'll call it seconds. Now we have to prove that it is a maximum. So remember, we're going to use the first derivative test. Here's my 2.04. Here's my v. If we take a number less than 2.04, like 0, we get positive. If we take a number bigger than negative 2.4, bigger than 2.4, we get like 4. We're going to get a negative number. So we know we're going to go up, we're increasing, and then we're decreasing. So our maximum height will occur at 2.04 seconds. Now the maximum height itself is, again, y of t is equal to negative 4.9 t squared plus 20t plus 150. So all we got to do is put in the 2.4 in for t and find out what our height is. And again, then we just take out our calculator and we find out what that is. And I get that it's 170 meters, 170.4. Which makes sense. It did go up, so it should be more than 150, which 150 is where we started, so it should be more than that, and it went up, and that's as far as it went up. Now, the next thing it wants us to find was it also wanted us to find when the stone hits the ground. Well, the stone hits the ground when the height is 0. So all we have to do is take our y equation, which was negative 4.9 t squared plus 20t plus 150, and set it equal to 0. At this point, it probably doesn't factor. My guess is we'd have to use the quadratic formula. So you can just use the quadratic formula. T will equal negative 20 plus or minus the square root of 20 squared minus 4 times a, negative 4.9 times c of 150, all over 2 times a. So we're going to get 20 squared minus 4 times negative 4.9 times 150. And we get negative 20 plus or minus the square root of 3,340 under the square root, all over negative 9.8. Sorry, my plus or minus doesn't look like a plus or minus. There we go. And then we're going to go ahead and take the square root of that to the square root of that. And then we're going to either add or subtract that from negative 20. So we get, and I'm not going to write it all the way down, but it's 57.79 roughly. Again, it keeps going. I'm not going to actually use that number. I'm actually going to take negative 20 plus that number and divide that by negative 9.8. The problem with that is it's a negative number. So the reason I say the problem with that is that time can't be negative, because that would mean it was before we actually threw the rock, and it doesn't make sense to say we're 3.9 seconds before we threw the rock on the ground. So we're going to ignore that one. So we're going to take negative 20 minus the square root of 3,340, then divide that by negative 9.8, and this time we get 7.9 seconds. And so it hits the ground at 7.9 seconds. 7.9 seconds after you threw it, it will hit the ground. We could find, and it didn't ask us, but we could find the velocity when it hits the ground. The velocity at 7.9 seconds would be negative 9.8 times 7.9 plus 20. So that'd be negative 9.8 times 7.9 plus 20. And I get that the velocity when it hits the ground is negative 57.42 meters per second. The negative is because it's down, because it's going downward. It's all that negative sign means is it's just heading downward. You don't want to get hit by that stone. So this is why they say don't throw stones at the canyon, because you could actually really seriously hurt or kill somebody if they've got hit by a stone going that fast. And that's antiderivatives.